Hi guys, this is going to be part two of the Earth Structure and Systems PowerPoint review. And we were talking about convection currents, and that is where things that are cold and more dense are going to sink, and things that are warmer are going to rise. They're going to be what we call less dense. And this happens in the atmosphere where hot air will rise. We have hot air balloons, etc. We have in water, the warmer water is going to rise, the colder water is going to sink down. And in the rock cycle, down inside the earth, in the mantle, in areas where it is more liquefied or more, a little more like a Play-Doh or just in a softer material, it's going to actually do the same thing. You're going to have the colder, more dense areas are going to sink, and then as they warm up, they're going to rise. But there was a hypothesis, which is an educated guess by a man named Alfred Wegener, and he stated that all the continents were joined together about 300 million years ago. Now, he kind of pretty much decided this by looking at the world map, and he got to thinking, hey, it looks like these would actually fit together. And so he didn't have a lot of science to back him up, but he just really felt like that was the case. His idea was rejected because he could not properly explain how the continents moved. Later on, to help him with his hypothesis, he looked at how the continents would fit together, but he also thought that, hey, it looks like the mountain ranges actually line up. Not only do the outlines of the continents seem to go together, it looks like mountain ranges could also connect. They found that coal fields matched. There were fossils on both areas, and there was a fossil called Glossopteris, and it is a fern-like plant found in Africa, South America, Australia, India, and Antarctica. And then there are also freshwater reptiles found in places that are now separated by oceans. So they couldn't really figure that out. And so once again, these all went into his educated guess for continental drift. And then also the climate played a role as well. There were fossils of tropical plants found on islands down in the Arctic Ocean. And obviously, the Arctic is very, very cold, so how is there a tropical plant there? And his thought was that this particular continent used to be in a different place where it was actually warmer. And so that was his thought. We're also going to talk a little bit here then about, whoops, I've gone too far. Let me go back. There were long mountain ranges found on the ocean floor, and sonar was used in the 1900s to map the ocean floor. And they found that some of these ridges have splits at the top. Now, when we look up on the crust of the earth, if we look up at the mountain ranges, we know that they have been pushed together because the plates are moving, and they're moving due to convection currents down inside the earth, down in the asthenosphere, that are moving. And as these move together, they're pushing and they're raising mountains. But on the ocean floor, it's actually a little bit different because the mountain ranges are there because the seafloor is actually spreading in those areas. And as the inside part of the earth comes up and begins to cool, it kind of makes like a big scar. It makes a lot of as this molten material comes out and cools, it creates a type of mountain. And those long mountain ranges are what we call mid-ocean ridges. And actually, seafloor spreading takes place there. And sonar was used to map the ocean floor back once upon a time, and they were helping to give some validity to Wegener's theory. More crust is added to the ocean floor at this place, and the older rock then is going to move outward. And when things are moving apart, this is what we call a divergent plate boundary. You will be asked this a lot of times in your education history. but divergent means things are moving apart, and we will go over that a lot of times. Okay, here's a visual of what we were just talking about. You'll notice as the convection currents are working down inside of the asthenosphere, which is the layer right below the lithosphere. As these currents move around, they're going to move the plates that were resting on top. And so as these mid-ocean ridges begin to move apart, the magma from inside the earth will come up and ooze out. And as it does, it's going to create a ridge. The older rock is going to be out farther away from this. And so as it moves away, it's going to be going toward the land as we know it. Okay, here's another picture kind of showing the same thing in just a broader view. And as you will notice, the Mid-Atlantic Ridge is starting to spread apart. This is something that scientists can actually calculate. They can actually watch this and determine how far things are moving apart. And if this went on forever and ever, common sense would tell you the Earth is going to get bigger and bigger and bigger around. The circumference would increase. But you're going to find out something about that in just a moment. So there's going to be a place not only where new flora is being created, there's going to be a place on Earth that we have found where some of the older crust actually disappears. So these happen at a deep ocean trench. And this is the area where ocean floor is sinking back down into the mantle. The newer crust is hotter and less dense, so it's going to float up on top. And then the older crust is cooler and it's going to be more dense. And remember, when things are dense, they sink. And so this oldest crust is going to sink. So when the plates collide, gravity is going to pull the old dense crust beneath the trench and back into the mantle. So you have a process here where new crust is being created, but then the older crust is then being recycled back down into the earth. And this is what we call subduction. It is getting subducted. You've heard the word abduction, where something is being taken away. Subduction is where this old crust is being taken away down at the deep ocean trench. As the subduction occurs, crust closer to a mid-ocean ridge moves away from the ridge and toward a deep ocean trench. Seafloor spreading and subduction work together, and this is because as these come together, they are converging. So we have already talked about the word diverging, where these things are dividing or spreading apart. Converging is the opposite. It's where things are coming together. And this is a convergent boundary. As you know, you're going to be asked this several times as well. So I would really get these firm in your mind, convergent and divergent. Once again, here's a picture showing the same thing. It's kind of a broad view. You see the molten material where the convection currents are taking place, where they are cycling around. You'll notice right in the middle is the mid-ocean ridge. This is going to, they're going to be moving apart. That's new crust that's there. It's moving away from the mid-ocean ridge, and then the older crust is being drawn down under the continental crust. It's being subducted. Once again, you have an illustration, much the same. And there's another one, a couple of interesting terms on here that we will be talking about. One is we have the convergent boundary and the divergent boundary, but transform boundary is the third type of boundary. So we have plates that are moving together are converging. Plates are moving apart, that's diverging. What's the other thing they can do? They can slide next to each other. And so they're sliding back and forth. And that's what we call a transform boundary. It's important to know that at a transform boundary, there is no new crust being created. There is no old crust being subducted or destroyed. And so at a transform boundary, it's just movement at that point. It's also called a transform fault. So then we come up with a theory of plate tectonics. A theory is stronger than a hypothesis. A hypothesis is an educated guess, whereas a theory is a lot stronger. This is something that's never been proven wrong. It hasn't been proven right. That would be a law, but it's never been proven wrong. And so we have a plate tectonic theory that is backed up by science, and we have instruments that measure these. So this is the theory that encompasses all the knowledge of continental drift, seafloor spreading, and the Earth's plates. So the fact that we know that things are moving around, we call that plate tectonics. We never knew why the plates would move around, but now we've found the culprit, and that is the convection currents down underneath, down in the asthenosphere, which once again is the layer right below the lithosphere. This is where the convection currents are moving around and the plates are floating apart or together, or they're shifting side to side. Now the mid-Atlantic ridge is moving just a little bit. It's like one or 2 centimeters per year. And a lot of times we compare this in class to how fast your fingernails grow. That's about how much that the new seafloor is being created. And that's what scientists believe. Other plates move a little bit quicker, and that could be up to 12 centimeters each year. And they can measure this with some of the fancy technology that they have. But this plate movement produces earthquakes, volcanoes, mountain ranges, and deep ocean trenches. And so that's why this theory is so important, because it gives some validity to other people's ideas. Convection currents, as I stated earlier, this is once again an illustration. I think you really need to have these really solid in your mind, just knowing that heat is going to rise, and then the opposite of that, the cooler things are going to sink. And if you think about the core being the hottest part of the earth, that's where things are going to heat up and they're going to rise, and then as they cool down, they're going to sink back down. And this is going to be a whole circle, a whole cycle. And so this cycle is what is going to move the plates. Once again, this is just another illustration. Once again, another picture that shows the mid-ocean ridge where it's spreading apart. If you notice in the middle of the screen, you notice what is moving the oceanic plate to the left. It's the way the cycle is moving. It's moving it to the left. And on the opposite side, it's moving to the right. And that's pulling the plates apart. Okay, and these are the 3 boundaries that we discussed earlier. The divergent boundary, it is a literal boundary. It's an actual place where 2 plates meet and they are moving apart. Convergent boundaries are moving together, and the transform boundaries, they are moving side to side. And then this plate movement is going to create an area where the crust is cracked due to the stress of that plate movement. And this can occur anywhere else in the plate. It can happen at a plate boundary, or it can happen anywhere else in that same plate. And that's what once there's a crack, there's a fault there. This breaks them down a little more. The divergent boundaries, it's important to know this is mostly occurring at the mid-ocean ridge. It's where the plates are moving apart. And then when the mid-ocean ridge rises above sea level, volcanoes then are going to come out. And that's probably going to create some type of an island at some point, because the magma is not going to be cooled as quick, because it's not going to be coming straight into water and cooling that off. But also, there are deep valleys on land, and these are called rift valleys. If you've ever had a rift with a friend, it means that you've probably had some type of argument where y'all aren't as close as you once were and you're coming apart. That's also what we call a rift valley. When you're on Earth and you have a deep valley, that's a difference. The main thing to remember when you're answering a question about rift valleys is that this is happening up on land where it's not in the ocean. And that's the easy way to remember that. Okay, the convergent boundaries. This is where plates are going to be subducted. This happens down at the deep ocean trench. And obviously the lighter, less dense area is going to rise above the older, denser plate. So when two oceanic plates come together, whichever one is older and denser, gravity is going to affect it more, and it's going to be pulled down underneath. If oceanic crust meets continental crust, the oceanic crust is always going to be more dense, and it's always going to be subducted underneath the continental crust. But when two continental crusts meet, they're going to push up because neither is dense enough to sink. There's going to be a high mountain that will actually rise from that. And if you'll think about that a little bit, it really, really does make sense. And then transform boundaries, as we discussed, these plates are uneven and jagged, and if they are rough, they're not slick and smooth, they're going to probably catch on each other. They're going to hook or lock onto each other. And that's fine. That may keep them still for a while, but at some point, that pressure is going to build up, and they are going to break loose or unlock, and this is going to trigger an earthquake. Once again, like I discussed earlier, crust is not created or destroyed at these boundaries. If we have a house sitting on top of one, yes, it's going to be destroyed, more than likely, but the crust itself is not going to be destroyed or created at a transform boundary. Okay, that was the conclusion of part 2 of the Earth Structure and Systems PowerPoint. As I said earlier, we're going to be talking a little bit about some of these in more detail as I go over each particular standard, and that will give you a little bit of review for each standard. But this is just a basic overview that I wanted to do for you. Once again, I hope you're being safe and staying well. I want you to know that I definitely miss you, and just in being totally honest with you, it's a lot harder to do these without the interaction, because I like to see your faces and I like to hear the questions that you have to ask. But either way, I want you to know I do miss you, and that was the end of part 2.